We kind of hit this right off the bat yesterday. Here you can see the Greek word electron right there. That was the name they had for amber, stuff that tree sap, whatever, that stuff that traps dinosaurs, and we have stupid movies about them extracting DNA. So that goes all the way back to the Greeks. Um, Magnetics. So realize that when we hit the magnetics unit, after this, magnetic forces are due to moving charges and only moving charges, with the exception of some magnetic materials uh, that they used to call lodestones that make compasses out of. So the other day that was Faraday from the movie, Maxwell and all that jazz, and then Einstein built his case on that. So just basic history again, a few extra bits from uh, the history. Now, important stuff. Uh, Obviously, Newton knew about gravity. That's late 17th century. Um, the 19th century stuff was the Faraday stuff, so it's stuff we saw in the movie. All right. And then in the 20th century, uh, we get to these weak and strong forces. So hopefully you had something in chemistry that talked about this, but it should be the case that protons in the nucleus of an atom would never stay together, but they do. Uh, the electrons and the protons you think would attract and combine with one another. They don't. So the strong nuclear force ends up being about 1,000 times bigger than the electrostatic force uh, of the electrostatic force. And so only when you get to the size of something like a uranium atom, which we also saw in the movie when Meitner was doing her stuff, okay, uh, that's when the atom, a nucleus becomes unstable. Uranium 230, it's either 5 or 6, I can't remember. It's one of the isotopes of uranium is the first one where it's unstable, where this thing, if you hit it just right, it's going to fall apart. And the way you hit it just right is one more neutron at the right energy level. And so then you can overcome that strong nuclear force, but it takes a humongous amount of energy just to make it in the nucleus. So just think about how much energy would it take you to climb to the top of this hill out behind the building? Any volunteers? I don't want to do that. Okay, my knees would give out on me before, or one of my knees would for sure. But anyways, that would be a difficult task. Even if you're in decent shape, you're still going to put out a lot of energy to do that. Okay, it's not easy. So getting over a hill is an excellent way to understand the strong nuclear force. And this nice little graphic here, uh, shows how we were hitting on these things, into the middle of the 1800s. And then the stuff got solidified between there, and that next century, century plus. Electroweak force, they get unified. So what's interesting is you have um, these things all getting unified into a combined force. They all wrap up nice. This nice little well-behaved Russian doll of forces. Okay, and then there's gravity that just isn't going to cooperate. We don't know how to link it. Maybe quantum physics will do it. We don't know. It may not ever work that way. So it seems that the gravity, the way that it's structured, is not going to correspond to, because gravity exists. There's mass because of the Higgs field. Mass uh, collapses on itself. Or the structure of matter is electric, essentially. So why they don't connect, I don't know, but they don't, at least not yet. So just history background there. Um, we are hoping that there is a thing called the graviton. We've detected gravity waves just recently, this decade, last few years, um, but no graviton. So we have all of these um, photons. Literally, there's exchanges between protons and electrons in a nucleus. That's that's why that structure is there. There's this constant exchange of photons. So electrons going higher and lower in their orbit. All right. Then there's these other things, gluons and bosons. Physicists have a sense of humor, um, and these are nuclear forces, strong and weak nuclear forces. The weak forces largely do with radiation. Okay, so you can get radiation from nuclear bombs, you can get radiation from nuclear reactors, you can get radiation from bananas. All right, X-ray machines give you a little bit of radiation, and the weak force describes that. Strong force is what holds everything together. If if somebody could turn off the light switch of the universe, like remove all the photons, okay, you could literally have all the material universe literally fall apart instantaneously. So if God was really mad one day, he could turn off the light switch, so to speak, and poof, everything literally falls apart. So there's that. I guess it's worth saying um, we sort of knew this already with gravity. So the whole sun Earth connection, I think it's worth, because people get this wrong when Jay Leno asks the man on the street interviews and they try to embarrass people. Why do we have tides? It's actually a tug of war between the sun and the moon. Okay? The moon is what makes our tides tolerable, and it's this dance. So when the moon is between the earth and the sun, it's there's a pull, and when the earth's between the moon and the sun, there's a different pull, and it's just right. Little Goldilocks zone there. Okay? If the moon was farther away or bigger or smaller or not there, if it wasn't there at all, we'd have insane tides. There would be no beach to enjoy. Okay, yeah, with the telescope, that's how you enjoy the beach. You stand up on a hill and watch it. Okay, so this little history there. These forces. I think it's important to know that we don't know of any limit on the distance. It's just that obviously with the inverse square, distance squared, it doesn't take long before the distance makes it makes it negligible. So, the gravitational attraction, if you were out in between galaxies, there's nothing really pulling on you gravitationally, at least effectively. You could conceivably just sit there and not be pushed or pulled in any direction. Technically, that would be false. There's some infinitesimal small amount of gravitational pull, and gravity's very weak as well. The weak force, this thing that's dealing with just the atom, really small scale. It's not even bigger than a proton, is the distance that the weak force acts on. And then the strong force is literally, a nucleus-sized thing. And so if you have a nucleus, okay, and some particle, let's see here. So then you have, like, say, some electrons out here. And if some particle wanted to get in, it has quite honestly, the energy hill, it has to really, on an energy graph, it would really have to climb high on energy to make it into the nucleus. So even if this thing was strongly attracted to either the nucleus or the electrons, it's not going to get in unless it's going at a crazy speed, humongous energy. All right. So most things don't make it here. They can't get up the hill. They dead end. All right. All right, we did this last semester. Gravitational potential, this is literally, uh, uh, what changes when I go from here, whoops, to here? Well, I lost an r squared, or I lost an r. So gravitational potential is literally force times distance, or work. That's all. That's what I mean by potential. And so, for in gravitational terms, we like to use the letter U for any kind of potential: spring, gravity, electric, etc. It's just work. And so it's the force times the distance. And if you multiply Newton's equation of gravity, force times distance, one of the r's, you lose an r in the denominator. Instead of inverse square, it's just an inverse function, power 1 inverse. All right. So just kind of going back to what we had done before, um, uh, there's that. Now, so this is work, and then if I were to do work per one of the unit masses, I would have a different kind of thing, and that's we're going to take on a walk here in a minute. So charge, you knew about charge before you came to college. You learned more about charge on Monday when we did the sticky tape stuff. You learned more about charge today when we were doing the charge into the field lab, and there's a ton of stuff to learn about charge. There's some complexity to the way those things interact. Um, and so you know about lightning, all this stuff. So this is no notes to take here, really. This is just as like, yeah, carpet, static cling, lightning. There's charges everywhere. Everything's got charge in it. Usually most objects have a neutral charge, same amount of plus as minus, and then that changes due to some interaction. All right. So I was just saying they have equal amounts of positive and negative charge. Most things are neutral. Okay. So I think you knew this from chemistry, right? Excess of electrons means it's negative. A deficit of electrons makes it positive. So it's one of the key conceptual mistakes that people make and think, oh, if it's positively charged, it must have more protons. No, that would mean it's not what it is. If I added more protons to a copper atom, it wouldn't be copper anymore. It'd be something else. So we don't actually remove positive charge. It's just a deficit. So one way to think of charge is just excess or deficit of electrons, because those are the things that are free to move in matter. No other charge is free to move. If protons moved, you don't. You have fission. If the protons move. So usually people don't struggle in this course with that because they work that out in chemistry. But it's easy to do, right? All right, not doing the demo. You basically did this with sticky tape. So an electroscope is used to have them, but they're easy to break. And when they break, then they don't work so good. And sticky tape is hard to break. And if you do break it, so what? You're out a penny, maybe. Okay. So the other day, but this picture is I want to start thinking about how you would pay attention to these charge diagram, if you will. And so if these rods in here, so this, you can't really see it so well in the picture. Look better when I've had it on PowerPoint. But so charges build up on surfaces. And so that's what's keeping this yellow arm away from the green arm is that it's repulsed by the other side. Same thing down here, so you have a kind of an equal thing there. So it's doing work on the mass of that arm. So I just came around, well, you guys were in lab, and I noticed that there's this electric force and then there's this gravitational force. I was showing you that with the sticky tape. Two attractive pieces of tape, one of them hanging between two books or something. I bring the other one there, it lifts it. So that was the attractive version of this. This is the opposite of that. So if I knew, say, the mass of that arm that's pivoting in this electroscope, I could figure out the magnitude of the electric force. And then I could use Coulomb's law to figure out what the charge on those must have been. Okay, so just a little talk because I'm tired of breaking these. Okay, so I haven't ordered new electroscopes because they get abused and they break. And of an electroscope, let's talk about the kind of make a comparison between what we did in the sticky tape lab versus what this explanation here is. So here's this claim: electrons are transferred from fur onto plastic rod. So let's say, I think I have them somewhere in the back room, got a stick. So it could be like this ruler. And then if I took somebody's sweater or whatever, the hoodie, you could rub it on here, and I'm going to transfer charge. When you pulled tape off of desk or tape off of tape, you literally were ripping free electrons from the surface. Okay? When you drag your feet across the floor, you're literally ripping free electrons from the carpet or whatever you're on. Usually don't get so much charge from tile and whatnot. But carpet, you can pick up static charge because you're literally pulling electrons off. You probably on the sticky tape, I'll show the calculation some other time, but when you rip those tapes, you're pulling about 1 in a million electrons off per surface. And it's all surface level stuff. Okay? You're not pulling it from the middle. So friction is an electron ripping off thing. So going back to last semester, friction, we're not sure we entirely understand that force. We measure it fairly well, but to what degree is it better described in terms of electric forces or some other thing? Obviously, the structure of matter is described in electric forces, but friction is it's somehow overcoming that electric force, or what is, they call it triboelectric if you were to Google that. If you can't sleep, Google that term and you'll wake up. Oh, wow, that was great. Okay. You could also do glass to silk. Okay. And so some transfers give us positive and some transfers give us negative. And the reason for that is the difference between the materials. Duh. Some materials have an excess of one thing and a deficit of the other. Does it really matter whether it's fur and plastic or glass and silk? No. It's not like that knowledge will transform your life into something. It's just sort of there's different kinds of material in the universe, and they carry different charges. Of course, you knew that from chemistry, right? How many electrons in your outer shell of this versus that? Why do some things conduct electricity and others don't? It's because of the free electrons. We're going to have a lot of talk about conductors versus insulators. All right. So the other day, you made an electroscope with sticky tape. All right. And the reason we did it with sticky tape, when the equipment doesn't work, that's irritating. So, all right, law of charges. So we did this basically. like charges repel and opposite charges attract. I think you probably knew that before you even came to college. Most people do. We verified this with the sticky tape. Do you guys do anything in chemistry that verifies that, or you just kind of take it for granted? That's fine, because it's not really that important to chemistry, fundamental at least. All right. Um, I guess the thing, if it wasn't obvious, is gravitation is always attractive, whereas electricity is attractive and repulsive. And that's because we have plus and minus charges. Gravity, we don't have plus and minus masses. Okay, obviously you don't have a negative mass. Doesn't make no sense. So polarization. Um, you surely you dealt with polarization as an idea in chemistry, correct? Water molecules are dipoles. There's a polarization in them, and so one of the reasons that there's always some sort of thermal heat value to everything in the universe is basically most things are experiencing some sort of polarization which stretches a molecule. And if you stretch something, it's sort of like bending a metal hanger. You're going to make it hotter because you're making things wiggle. And the more they wiggle, the hotter they get. Okay. So polarization basically, so if I have a big plus charge and I bring it near something that's neutral, well, guess what? All of these minus charges, they want to get over there. And all of these plus charges, they want to get away. Oops, a different color. So these, they want to get away from this plus charge over here. So one of the things we're going to have some in-class stuff soon on um, how charge transfers by conduction and polarization, and thinking through this kind of process and understanding a transition from neutral, which was what the thing with the surface charges was before that plus cube was brought near. All right. And in general, if it's a uniform shape, we'll get to this eventually in this. So like a sphere, charges will spread out equally. If you have excess charge, everything will get equal distance from one another because everything wants to be as far apart from another like charge as it can be. Now, if the shapes are regular, like if it has a sharp curve on it, then things tend to pile up on the curves, the sharp curves, and spread out everywhere else. So there's some interesting feature to deal with there. All right, just some factoids here. I've been talking about this Coulomb thing. All right, and probably the elementary charge slide's coming up, but I'm going to write it here. Is elementary unit of charge, which we saw on Monday, is essentially 10 to the minus 19 coulombs. And as the example we showed on Monday, 1 coulomb is a lot of charge. It's a deadly amount of charge. Okay. And what in the world is this? Good question. Glad you asked. You've heard of amps, right? That's what the big A is. That would be 1 coulomb per 1 second if you were to just kind of do that math there. So one of the things we're heading towards, the kind of the pinnacle of our exploration of electricity, will be to deal with circuits. And in circuits, there's current flow, which we do measure in amps. 1 coulomb per second. Well, 1 amp will kill you. In fact, you get close to 0.7 amps, that's like the deadly zone. So we're going to deal with circuits that are usually probably 30 or 40 amps. No, I'm just kidding. Uh, we deal with milliamps. Okay, most circuits run on that kind of charge transfer, which worst thing it's going to do is make you go, ow, like a little. If you've ever been kind of shocked, shocked means you survived. Electrocuted means you didn't. Okay, so these are powerful forces. So just one personal example: I was in the Navy, operated nuclear reactor plants on submarines. And in a reactor plant, you have all sorts of things. You have mechanical systems, electrical systems, control systems, all that jazz. And there was one work job that I was the QA person on, and it was an electrical job. And we have these procedures, and somebody got shocked because somebody else violated. We had tagged out a system. You have all these danger tags, don't operate it. Well, somebody thought they needed to do something, so they violated. That person got in a lot of trouble. And the reason they got a lot of trouble uh, wasn't just because they violated the rule, but this person that got shocked lost 3 of their toes. And so as you come out of the area, when one of these incidents happens, the protocol is you have to take off your gloves and stuff. And so often what happens in these cases is that fingers or toes will be left behind in the gloves or the boots. And you won't even know that you've lost them until because it cauterizes it, and you're shocked. So your body's in that. And so this guy, and we do it. You take your boots off and you dump them out, and out came a couple of toes. And, and once they're cooked like that, they don't go back on so easy, and that changes your life, especially, if you didn't have a big toe, your walking would be impacted dramatically by just not having a big toe.
Would that person who lost his toe, would he not be able to be in the army?
No, you have a prosthetic or something like that, but so it's these. So this is, these are powerful forces, and so that's the other thing too about that lab. There's a little bit of pain and suffering just in getting those things to be on the line and whatnot, and you notice that really small distances have humongous changes. Okay, and that's one of the things about that was just to get that into your head about these forces. So on Monday, I talked about these insane accelerations that an electric field will put on a small mass. Then you can kind of see it in the simulation, and then this discussion about what an amp is. And 1 amp will kill you. All right, so be careful. It's hard to do this. There's not many places where you can go and experience 1 full amp. Okay, but it's happened. Those people are dead. All right, there's that elementary unit of charge. Takes a lot of electrons to add up. You'd need at least 10 to the 19th of them to get 1 coulomb. A little bit less than that, 10 to the 18th or so. All right. So, and this is what Millikan figured out a while back, about a little over a century ago, early 20th century. All right. Like I've been saying, full coulomb, a lot of charge. So a piece of lightning, 10, 20, 40 coulombs in a split second. All right, so a humongous amount of amperage, hundreds to thousands of amps. So if 1 amp will kill you, people do survive sometimes.
Were they just shocked still?
Well, it's how much of it actually went through them. So it might have gone through something near them as well. So it's
So they got shocked by lightning.
they got shocked. So here's a calculation of how many electrons it would take to make 1 coulomb. You just do the math. So 10 to the 18th, that's a million trillion. The Milky Way galaxy probably has 200 billion stars in it. So 1 coulomb of charge has more electrons than there are stars in the Milky Way. 1 coulomb of charge has more electrons in it, 1,000,000 more electrons in it, 1,000,000 times more electrons in it than there are galaxies in the visible universe. There's about 100 billion visible galaxies. This is insane. All crammed into a small space. Okay. So our simulation, we were dealing with nanocoulombs in that cool little simulation environment. When you were pulling the tape, we were dealing with probably micro, somewhere between micro and nanocoulombs, closer to nanocoulombs. So sticky tape would be that realm of charge levels. Talked about Ben Franklin a little bit the other day. It's interesting. You don't expect that these people know more about Franklin as a politician than they do as a scientist. And he was an interesting dude. He was a party animal, a little bit of rock star. He had a lot of girlfriends, and he had some funny ideas. Um, but he was right. Like there was one thing he used to do. This is kind of weird. He would sleep naked with the windows open in the winter because people used to think that the cold would give you the cold, and that's false. Uh, if you get too much moisture and warmth in that presence, then that's where the breeding ground is warm, moist places are where bacteria flourish. And so he actually was almost never sick because he would do weird stuff. Or he was really smart though. He figured out, he's like, no. Cold keeps me from getting a cold. So he was an interesting fellow for sure. Uh,
Cold environments though, where like bacteria and all that kind of hang out as well. Because I know, like, say, like if you're in Minnesota, a cold house, if one person's sick,
well,
everybody
that's because you're in a closed, warm environment with limited ventilation. So it's an airborne bacteria.
biological bacteria breed at 37 degrees Celsius,
Yeah,
body temperature.
yeah. Yeah. Generally speaking, those sorts of things need a warm environment. There are some extreme, they call them extremophiles that exist in extreme cold or heat, but those are rare. You have to go to sea vents and or the ocean and places like that. Your house is not a location for extremophiles, unless the people in your house are into base jumping and stuff. But that's a different kind of extremophile. A little sociology joke there. All right. Total charge is constant. It has to be if it's conserved. Okay. Total charge, you name it. All right. This oil drop experiment. This is what some dude in the early 20th century did, just after the turn of the century, World War One-ish. Uh, and at this point, people had figured out a lot of the periodic table, but they were trying to understand the structure of the atom still. And we weren't sure about this charge quantity. What is it? And he figured out if he atomized some oil and used electric fields. Remember how I was just showing you? There's a reason why these things are staged this way. That sticky tape thing where I levitated one piece of tape with another without them touching, it's essentially what this is. Except this can that he built uh, used electric fields to kind of suspend these really light oil drops. And so he knew what the oil drops weighed. Okay. And then these x-rays would interact so he could see these atomized drops levitating inside of there. So I've oversimplified the experiment a bit to make that point. But so we did our little version with sticky tape. All right. Using this apparatus, he was actually able to figure out what that fundamental unit of charge was, and then the things in chemistry really started taking off in a new way, and physics as well. So, think you probably know about the structure of atoms by now from chemistry. Is that safe to say? All right. I don't think we need to go over the fact that protons are in the middle and electrons are on the edge, and neutrons go in the middle too. All right. So I'm going to gloss over that. I think this stuff is also old school stuff, given everybody here has had chemistry, so I'm not going to labor that point. All right. Net charge. So here is a problem. Might even see something like that in homework. Suppose we want to create a net positive or a 10 microcoulomb charge on a block of copper metal, 2 kilogram block of copper metal. What fraction of electrons in the copper block would we remove? So first we need to know what's the number of copper atoms. Hopefully this calculation is somewhat reminiscent of stuff you did in chemistry. Okay? If I know I have this many kilograms of copper, I have to do this Avogadro's number gyration. There's no other choice unless you have some mutant power that lets you count atoms by looking at it. Okay? So we go through this rigmarole and we get this interesting number, 2 times 10 to the 25th atoms in that mass of copper. You should have done plenty of these calculations in chemistry, so I'm not too worried about that. Then you're going to use that chemistry knowledge. Atomic number is 29, which can only mean one thing: 29 electrons per atom. So 29 times that number we just did gets us to a new number of electrons per atom. And so if we want to uh, uh, get that fraction, then we say, well, there's 10 microcoulombs is 10 times 10 to the minus 6. That's what that number is. So in fact, I'm going to change my color up here. That's what we mean by 10 microcoulombs. Hopefully you're familiar with the micro nano multipliers. Then there's this fundamental unit of charge. So we come up with how many electrons would give us that 10 microcoulombs. And then those things get jammed together to get our percentage. So this number conveys to there, and this number to there, and we get this insanely small percent. I mean, how do you even talk about a percentage that small? 10 to the minus, is it 0.00000? That's nothing. Extremely small amount of charge required or removal. But we're also talking about 10 to the 13th electrons ends up being such a small percentage of the whole. So the size, a number of things that exist on the atomic scale, the molecular scale, so to speak, atomic scale of matter, is there's more there than there is in the big universe at large. Because 10 to the 13th would be like the number of stars in our galaxy, or the number of galaxies in the visible universe. 100 billion. Well, 10 to 11 is 100 billion, sorry. That's 10 trillion, 10 to 13. So we literally have galaxies worth of stars, like 100 galaxies. It's just nuts. This example, two reasons it's here. It ties your chemistry knowledge in with what we're doing in physics. It's always good when you can connect dots between topics. And then two, one of the drums that I want to bang is the magnitude of not only the forces on this scale, but just the number of entities, the objects on this scale. It's when there's that much, when removing uh, 10 trillion electrons from an insane number of electrons in just 2 kilograms of copper. That's not, go to Home Depot and grab a copper pipe that's a foot long. And you got your 2 kilograms. That's 4.4 pounds. Okay? There's a ton of potential work there in terms of electric forces and energy. So that's the takeaway conceptually is what I was just saying. Computationally, yeah, sure, you're going to do this once or twice. You already know how to do half of it, or most of it, from chemistry. All right, so moving on. Conductors are because electrons can move freely, and we're going to have a whole separate lecture devoted just to this called about electron mobility, but I'll give you a preview. You want to think of, so we have these lights in the room here. So like if I were to turn off this light that's on this bank here. So these are 120 volts. Think of voltage like a pump. And when I flip this light switch, so this light switch is kind of open, shut the valve, if you were to think of like a water system. And there's this copper pipe, a solid wire, running up through the wall over to wherever those things are. And in that copper pipe right now, and inside the light bulbs that are off, there's this sea of mobile electrons. Okay, in the copper, it's the free electrons in copper. In the lights, which are gas tube lights, there's just a charged gas in there, and the charged gas has free electrons. Well, it is free electrons, really, mostly. And so when I turn on the pump, I instantly get light. If it were incandescent bulbs, it'd be even faster. Okay. What happened is those mobile electrons are just kind of sitting there, kind of like a lake, okay, behind a dam. And if somebody opens that floodgate, everything starts moving at once. All right. And so the free electrons that were between this light switch and the light itself, that whole body of electrons is moving at about, well, at most, a meter per second, slower than you walk. You kind of have in your mind, well, gosh, these electrons, that's be zooming around at light speed. No. And especially after Monday, we were talking about these crazy accelerations they obtain due to electric fields. You'd think they'd be moving much, much faster. Well, realize they're very small, okay? And they have a very long way to go. That's what, think of people are small and the moon is a long ways away. It takes a long time to get to the moon, okay? Take us a day or so. Take us months to get to Mars. We're small and we don't get to move. And even though we can move fast, it's too big a space, all right? So same with free electrons. Plus, free electrons are constantly banging into things around them inside there. So it's not like they have a straight line path, all right? So just a little preview there of what's coming down. And then insulators, well, they don't have free electrons. So they don't conduct very well. Yeah, some things conduct electricity. Great. I'm going to skip past this. We talked about the LHC, Large Hadron Collider in Switzerland. It is a, yeah, okay. Yeah, it's 17-kilometer path length, but it's about 9-kilometer diameter circle. So they built a tube under the ground that you, if it didn't have all the toys in it, you could drive a semi truck around. You could have a semi truck chariot race, okay, in there, or get a bunch of UPS trucks and FedEx trucks racing each other. All right, that's how big that tube is, and they did that 100 meters underground. Crazy. All right, they did that to control temperature, radiation, etc. Uh, Plus, it'd be ugly above ground, and you can't have that. There's a nice lake there and everything. Plus, it's cool. Get to go down a big elevator and do stuff. So uh, we use superconducting wire in these electromagnetics thing or electromagnets in order to get contained. So literally, it's a huge magnetic field, all 17 kilometers of that path length. So those tubes inside of this tunnel are big tubes lined with electromagnets the whole distance. Okay, because we have to keep these charged particles on the circular path, and magnetic fields are what bump moving charged particles. So we increase the speed of those moving charged particles, and they're on anti-parallel paths, so they're going around opposite directions. And then once they're to the right speed, somebody flips the switch so that the magnetic fields are on the same path, and then the next time around, crash. Okay, so enough on that. Anybody had an MRI? I think I've had one. My daughter goes to get one today because she hyperextended her knee, which was painful to watch. She's a gymnast. Uh, went back when she took a landing, and ugh. Thankfully, she did not tear her ACL. She only sprained her PCL, which is better because that's 6 weeks versus like 9 months when you tear an ACL. So, uh, but she's a trooper. Um, and so, what do MRIs do? Well, uh, nuclear magnetic resonance imaging. So if it's magnetic, it's electric. We'd have learned that much from the movie and the Faraday section of that movie. Moving charged particles produce magnetic fields. Magnetic forces only influence moving charged particles. Uh, Fixed magnets, uh, an example of that, or a slight exception to that. And literally, it does this by electric and magnetic fields bouncing back from charged particles. Well, guess what your whole body's full of? A bunch of moving charged particles. You have 85 billion neurons in your noggin. 85 billion neurons in your brain, firing up all the time. All right? So there's a lot of, that's why, this is a brain picture or a walnut. I'm not sure what. Some people, you're like, I'm pretty sure your head's a walnut. Okay, and nothing's moving in there. And we get nice pictures from that. But it took a long time for people to figure out how to decode those reflected electric magnetic fields and get a picture out of it. But ultimately, it boils down to something like Coulomb's law. What's the size and mass at some distance based on this electric field that I just measured? And to get that precision from a small enough magnetic field so that we don't scramble your brain. All right. Does anybody wear or know people who wear the magnetic bracelets and they think it makes them pain-free or whatever? So here's the thing. We don't know for sure. There's no study that demonstrates the positive effect of that, magnetic bracelet. But one thing we do know, a magnetic field, a moving charged particle will be deflected by a magnetic field. And whatever circulation is in your wrist or wherever you put one of these bracelets, your blood's full of moving charged particles. Well, your whole body, your lymph system, your blood, everything, there's moving charged particles. So there is a magnetic field interaction with that moving charge particle. Is it enough to produce any health benefit? We have no idea. So there's a partial truth there. Yes, those things are doing something to the moving charge particles and whatever goes past there. Does it help you feel better? If you think it does, uh, uh, there's one thing for sure is a bunch of people think it does. Whether it really does or not, I don't think anybody's figured out yet. And I think it's because there's not a compelling reason, and they think those other people are silly. And there's not as much research money that goes to the biggest puzzles to solve. We've already hit this, so I'm going to skip past this and get to conduction. So I showed a picture of polarization. Well, the other obvious thing, if you've ever been shocked by somebody walking across the carpet, it's because they conducted the charge that they picked up from the carpet to you. And you either liked that or you didn't. Usually you don't. So when, prior to this rod here touching that plate, there would have been probably a neutral charge, but as fast as they can move, these charges will start to redistribute themselves, and they're all positive, so they'll get as far away from one another as they can, and that'll cause this electroscope to move, like that sticky tape moved in our lab on Monday. All right? So charging by conduction, you sort of knew that already. Here's a nice picture to go with what you already knew. Induction is this thing that happens without touching. It's essentially polarization. So what happens is as these positive charges come near to what was previously a neutral plate or a neutral system, meaning it had an equal number of positive and negative charges, then the negative charges will want to come, so there'll be a rush of negative charges wanting to get to this plate because they want to get to where the positive charge is, or the deficiency of negative charge. So one way to think of it is if I rip off a bunch of electrons from the outer surface, what have I done? I've just cleared a path to the protons. So that's one way to think of it. I peel off some electrons from the surface of matter. That means, oh, there are some protons. I can see a couple of protons peeking out, maybe. It's a kind of a metaphorical way to think of it. And so what that means is instead of there being a balance between a plus and minus, that minus went away. Now I have this positive. It's like I poked a hole in the wall, and now you can see where the nucleus is. That's kind of a crude way to think of it, but effective. And of course, they're not going to transfer across space. Well, it would take a lot of charge to break down air. That's what happens with a spark. The amount of electric field force to do that is pretty substantial. I forget it off the top of my head. We'll get to it. Those are all repeats. Should have taken those out. We did this already. Talked about this constant already. That's the more precise version, but literally 9 versus 8.99. Really, technically, that's the value. We have not covered why K is that. All right, but I want to give some attention to this E naught thing. Okay. Epsilon naught, electric permittivity of a vacuum. Okay. Permittivity, meaning how much does space have a capacity, the empty space, vacuum space, like outside of our atmosphere? How much does it let electric fields do their thing? So the electric permittivity constant, which is the fundamental part of the Coulomb constant, K, it is a fundamental property of space itself. All right. The thing that we didn't show in the movie, but they sort of halfway talked about it, is that the speed of light ends up being the square root of 1 over this permittivity constant and the same kind of constant for the magnetic permissivity of free space. So free space has two fundamental constants related to space that talk about its capacity, so to speak, for electric and magnetic fields. And so the speed of light being constant is actually a structural facet of space itself. That's our best knowledge. All right. Well, might be a little better than that, but it hasn't changed for over a century. All right. Well, speed of light hasn't ever changed really. It has to be constant, otherwise we wouldn't be here having this conversation. But there have been people who think the speed of light's been slowing down, and they're kind of crazy. But K, we didn't cover this the other day, is actually this right here. All right. And it's still that 9. K is 9 times 10 to the 9th, but this E naught thing is a different number. We're not going to deal with this much. This is not really that important to our work. You're going to use that 9 times 10 to the 9th thing a bunch. Why is there a 4 pi bottled up in this K? Possibly because that's the surface area of a sphere, and we imagine them as spheres, and who knows? Well, some physicists know, and you can go take a whole series of courses about it if you want to become a physicist, but that ain't going to happen. So we did this calculation the other day. What's the force between 2 Coulomb charges? Well, 1 Coulomb squared, 1 meter squared, basically is the same as the Coulomb constant. Well, we already did Monday. Again, this electric force thing, we finally got to use it today in the second lab in our work calculation. So I think one important thing more, because this is a review slide, but just remember, work is always the change in kinetic energy. Work is always force times distance. Kinetic energy is always half mass of final speed squared minus initial speed squared. It doesn't matter what force we're talking about. Gravitational force, spring force, buoyant force, electric force, magnetic force, it doesn't matter. Whatever the structure of the force is, you'll put it in there. So for, in our case today, our force was the electric force, K, Q times some other Q, D squared times D. And of course, that means those cancel. And you basically have, a different calculation to do. And of course, in your lab, that was 0 because it was starting off at 0. So you could solve this thing for V given all these other things and the mass. All right. We had a little bit of review or this sort of talk in our Monday lecture, but it's going to be important that you stay proficient with realizing that at some position like that one, there is a position vector, R1. And at some position like this one, there is another position vector, R2, relative to the origin. And that since these are charges interacting with one another, there is a vector from one to the other. Okay, that's what, R would be in this case. It'd be the difference of those two vectors from the final location relative to the initial location. Or in our case, it could be source versus observation, going back to what we did on Monday. And of course, the unit vector definition, that comes from last semester. All right. So we'll want to remember those computational things. They're simple things to do algebraically, but if you don't remember them, then it's totally black box. You don't know, you're kind of stuck. And so we even, this is a review from Monday as well. A lot of a review in this thing, and I'm doing that on purpose because this is not the easiest steak to chew. Am I right? There's a little bit of complexity here. So we got time, so we'll take time so we don't kill anybody. Please recall, a net force is always an adding up of all of the interactions. And so notice in here that the net force on one thing always involves that one thing, and the net is always going to be summing up with respect to all the other things that are interacting with that one thing. In fact, on Monday we talked about how the superposition principle, we add up all of these things in Vectorville as if every pair of things we're paying attention to, that's all there was. This to that one, this to the other one, this to yet another one. We add all that up and we get our answer. Okay. An example. We did helium the other day, didn't we? So let's revisit. What is the magnitude of electric force between two protons in the helium nucleus? It's a simple nucleus. It's got two protons. What is the magnitude of the electric force between those two protons? Well, distance, we could look this up. We're giving it away here. 10 to the minus 15th, is that an angstrom or is 10 to the minus 10th an angstrom? I think 10 to the minus 10th is an angstrom. But 10 to the minus 15th is essentially the width of the nucleus, about as far apart as they could get. That's knowledge that we should know by now. If they were electrons, they'd be minus that. And then we just jam it into Coulomb's law. This charge and that charge, they're the same charge. One each, squared of that fundamental unit. Distance between them squared. 58 newtons. That's a lot. Okay? For something as small as a proton, which is 10 to the minus 27 kilograms, if memory serves me well. All right? 58 newtons in pounds force, well, 1/4 of that. So 13-ish, 14-ish, somewhere near pounds. So for something as small as an electron, 14 pounds on it, that's a big deal. What if the distance is doubled? Well, doubling in a squared thing makes it 4 times as big, which means you have 1/4 of the force. All right. So just going twice as far has a dramatic nonlinear change. It decreases it by that factor. So we have some conceptual questions where the whole point is to recognize that it's an inverse square. So if you double something, that's a 4th. If you triple it, that's a 9th, et cetera, et cetera. All right. How's our time doing? 11:15. Okay. Now we're going to start getting into some nitty-gritty things. And this is a clicker quiz, but we're just going to pretend that we're clicking. All right. So we'll think it through, imagine an answer, and then see what it's supposed to be. So here's these two charges, Q1, Q2. Q1 is that amount. Q2 is a bit more, and they're separated by 40 centimeters. That's the distance between them. Where do we need to put a third charge for that charge to be at an equilibrium point? Meaning the push and the pull is a 0 point, if you will. Do we put it, so you're going with A? Put it, so we have, anybody want to pick a different one? All right, we'll see what, where'd my answer go? So I guess here's a thing to think through. What's going to happen in the middle between two positive charges? There would be some spot. What's that? They're both pushing. So something could get stuck off center. It would have to be off center if it were in the middle, and if it were a positive charge for the push from the left to be the same as the push from the right. It'd have to be off center. Okay? So same with a negative charge. All right? Of course, with the negative charge, you'd expect the bigger one to pull it in. But the other one's pulling on it too. So it depends on where you start. But there's a spot where it would equilibrium out in the middle. Where do we need to put a third charge for that to be at an equilibrium point? And we have noted one dispute about the misleading middle term. So let's think about x3, I guess, less than x1, so that's out here. Okay? So, is this spot going to work? We get no equilibrium out there for the reason stated. Forces from Q1 and Q2 will always point in the same direction, so it's pushing it out. What about the next spot between x2 and x3, or that's C rather? I guess that's out here. All right. Same thing. No equilibrium. Review here. It's like, so it's got to be in the middle. I love it when I get the answer right. I might have looked before today, but it's the only place you could have it balance out would be in the middle, regardless of the charge value. It has to be in the middle. Now, the exciting part would be for you to do all of that math. Okay? And just hold off on volunteers. I know that you're eager to do that. But you may want to come back. I'm pretty sure that there is a homework problem or a quiz problem involving this. Okay? So let's just think through what we have here. What is this? I mean, what is it a version of that we've studied recently? Coulomb's law. And the distance, the only thing that's different in the bottom there is that instead of it being a d squared, it's a difference in positions, which is a distance, squared. If we knew what x1 and x3 were, okay, then we could actually put a number there. Since we don't, we have to stick with these variables, all right? And then this right here is also Coulomb's law for the difference in the other position. Nice thing, though, they both have this common term, which means I can, in this equality, because there's an equilibrium point, so I want to make this case here. When I say equilibrium, there's a reason why the equal sign works for that. When is the force on the left-hand side equal, or actually, not when, where is the force on the left equal to the force on the right? Okay, well, it can't be only if the charges are same magnitude. Your feeling is noted. And okay, so this is a seemingly complex algebraic thing, and it's a little tedious from an algebra standpoint, but I wanted to decode the problem a little bit and point out there is a simplicity here. If there's equilibrium, meaning a spot where the forces are the same from both directions, it has to be this way. Coulomb's law at some location, some distance equals Coulomb's law at some other distance. And it has to be different because we know that Q1, Q2, and Q3 are all different charges. All right? So the rest of this, you'll come back and just look at this if you need to copy it, but, all we're doing is solving for x3. Somehow, all of that boils down to x3 is this lovely little fraction, complex fraction. But once you have it, we knew Q1 and Q2, all right? And Q3 drops out. Isn't that a bonus? Both sides gone. I gotta switch to, otherwise that would be really hard. Okay. Plus we weren't concerned what the magnitude of that charge was, just where would it be equal? Because would it matter what the magnitude of the charge is? No, it would matter where it's at. So let's go back to the original question just so we can kind of, so we get this interest, so 0.16 meters between. No, we said where? Well, qualitatively somewhere in the middle, but you would expect it to be off center. I think the point is that it has to be off center given the two charges aren't the same. Okay, if we needed to, and sometimes we do, then we would compute it, and it would involve this semi-tedious algebraic gyration. All right, so you may want to refer to this slide 41 in the near future. I have to put up the handout from Monday, which means I'll do it today along with this one. Now for something a little more complex. So let's say that we had two ping pong balls that were charged or something and hanging on a string. And if they were charged in the same way, then they would repel one another like this. And there would be some angle of deflection. All right. So here's some data, so we have, the length of the string is 1.5 meters. Both of them have 25 microcoulombs on them. The angle ends up being 25 degrees. What is the mass? All right, so let's take a moment and consider what it takes. Obviously, you need to think. Sometimes that happens in school, okay? We need to draw pretty pictures, which I provided a pretty picture, so that you can model it properly. You might have to look up some stuff. Then you're going to do math without plugging and chugging. Because if you try to do all the plugging initially, you end up carrying forward rounding errors and stuff like that. So try to get a simplified thing, then all the basics. Calculate all the stuff we do, but we don't think about what we do. All right. So three forces. Okay, so there is a electrostatic force of repulsion pushing them apart. Okay? Each ball has a mass gravity thing going for it. And then there is a tension in the string. So hopefully those look like force diagrams that we did last semester. Only thing that's different is now what is causing the tension in the string. The electric force is causing a separation that produces a tension. And we would do the same sort of stuff before. We would, this angle, of course, hopefully you recognize that theta would be right there. Okay. What do they call that? Alternate interior angles or whatever. So here we get a nice free body diagram that's referring to this. So we go from a statement, a pretty picture in reality, to a idealization of that reality. And from this, we get to sum forces, get the net force. Okay. So this force here is, this is going to be a KQQ kind of thing. This is going to be an MG kind of thing. And then we'd have to solve for tension. So I'm banking on you remembering something from last semester. Okay. But here is the sum of forces. This is the sum of forces. Here, there's a portion. That's my T sine theta. All right. And I'm sorry, that's not T sine theta. That's T cosine theta, because it's adjacent to the angle. And that's T sine theta. So this is an x direction summing. And it's an equilibrium. It's not moving. So my MA equals 0. There. Then you do the y part, and you get the cosine minus mg, gravity. And so the nice thing here is that t shows up in the system of equations. So I can solve both for t, et cetera, or isolate it for t. So then here's the under the hood. You just thought you had made it easy, all right? So we know how to solve this. We've done that a couple of times now, but we do need to know more about this sign relationship. Plus, remember, we don't know this. All I know is how long this is, and I know what the angle is. And the only way I can do Coulomb's law is if I find out what's the separation between charge. The only way I'm going to get that separation of charge is to do trig, right triangle trigonometry, which you had a whole course on, or a course that involved it. So now, this equation here gets me to D equals 2L sine theta. So multiply both sides by 2 by L and you get D equals 2L sine theta. So now, this is my D. And at this point, if I remember right, we already know K, we were given Q, we were given L, we were given theta. That means that this now lets me compute the Coulomb force. Simple but tedious. So I want to, we weren't concerned with the tension, didn't need to find the tension. Okay, you know you're going to get a handout of this, right, Cameron? Yeah, I see. The nice thing about this is, well, obviously the t's drop out. That becomes tangent. I hope you recognize that. Sine over cosine is tangent. We just found a way to get the Coulomb force, combining the trig with our free body diagram. We already knew the mg part. So here we have this interesting thing where tangent theta works out to be this mess of things, and the only thing we don't know is mass. So we solve it for mass, and we just plug and chug. K is a constant, we're given Q, G is a constant, so it's 4, in case you forgot. L was given, theta was given. Pretty sure that there's a problem like this in the homework as well. So you'll want the video and the handout. The handout will probably be sufficient. Okay. In fact, I would expect that you may not have to do anything but change the numbers. Isn't that nice of me? Bore you to death in the lecture, then they give you the handout, so you just do plug and chug the math. So we go through all this and we get this amazing mass of 3/4 of a kilogram. And so we could double check, but I'm not bothered with that because I want to get to the end of this slide. You can review that later. One last thing here to finish up. I've mentioned how much bigger electric force is than gravity. One way to do that is to give a ratio of the Coulomb force to the gravitational force. So Coulomb per newtons, if you will, in that regard. And so we can put, realize here that this is one electron, or this is one proton rather, because this is the mass of a proton. I'm sorry, electron. My brain. So this is the electron part of the puzzle. Charge per unit mass. Later on, this ends up being an interesting feature of resistance. It's not fundamental to resistance conceptually, but it ends up being, you can pull it out. We'll get to that later. These are just constants here. New one this semester, old one from last semester. Important thing is the electric force is 10 to the 42 times bigger than gravitation force. 10 to the 42. How do you think about that? Well, if the universe is 14 billion years old, that's roughly 10 to the 17th seconds. If you could bust the Earth down, well, all the grains of sand on all the beaches is roughly 10 to the 22 grains of sand, which is essentially the same as the number of stars in the visible universe, 100 billion stars per 100 billion galaxies. Okay. If you could bust the entire Earth down into particles of sand, you have 10 to the 30-ish. Okay, so 10 to the 42, that's humongous. 10 to the 36 is a trillion, trillion, trillion. So this is real. This is a trillion, 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 trillion. Okay, it's a lot. It's a big deal. Uh, Here's an example. We're getting close to running out of time. You'll want to. This is also in the homework, I think. What's that? See? And there was much rejoicing. He's giving me the math for my homework assignment. Yes, I planned that. Um,
And this homework assignment, it's not like last semester, you don't have one every week, you just have one per unit, correct?
right,
Okay, I just wanted to
right.
double check, because I was like,
And we'll have 4 or 5 units in the course.
Okay,
So
only 4 or 5 actual.
yeah, right. But they're challenging, but the lectures will give you much of the work will be done for you in the lecture. And then you have it recorded and you have a handout, et cetera, et cetera. So your group work will be made more funner than it would have been otherwise. Okay, by design. So here's just another one, and to go over this quickly. Um, what is the magnitude of the electric force on Q4? This one, due to resulting from the remaining 3 charges. So here's this coordinate system where everything's 1.25 meters away, and then the diagonal 1.4 times that. Okay. So in the x direction, what do we have going on here? Let's just be clear. So Q1 here, Q4 there, the distance between them there. All right. And so all of this right here is what we have going on here when we plug in Chugsville. And so all that would be different, you could repeat that calculation down here, just with different charge values. Okay. Then in the y direction, same sort of business. I'm not going to, same pattern, but up and down instead of left to right. And the only thing that'd be left to do would be compute along the diagonal here. Anybody remember the multiplier along that diagonal on a 45 degree? Just a root 2, square root of 2 multiplier. I think that shows up here. All right. So when you get the handout, or if you want to pause the YouTube video, you can just read the math and use it. So all of this boils down to being able to obtain this really small number of newtons, and we're in business. All right.